and welcome. This is Safa. In this video, we'll explore one of the most powerful and elegant control strategies, sliding mode control or SMC. But don't worry, we're keeping it conceptual and visual, no equation yet. As we saw in the last video, PID can do well until something unaccepted happens. It doesn't know how to adapt because it assumes the model is perfect. What if we could build a controller that actually embraces the uncertainty? Imagine a surface like a ramp in the system's state space. SMC forces the system to quickly reach the ramp and then slide down toward the goal. That's where the name sliding mode comes from. The system slides along a design trajectory. Here is a simple analogy. Imagine a ball rolling in a 2D world. The controller's job is to push it toward a slope. Once it lands on the slope, the sliding surface, it naturally moves to the bottom. That's how SMC reduces the effect of disturbances. Once the ball is on the slope, small pushes don't matter anymore. SMC is powerful because it doesn't need perfect models. It said, just get on the sliding surface, I'll take care of the rest. And it graduated convergence, it's finite time. That's huge. But one challenge we'll explore later is chattering, high frequency switching, which we'll handle in future video. This makes SMC perfect for systems like AUVs, which constantly face uncertain water currents, pressure changes, and limited model accuracy. That's why it's used in aerospace, underwater robotics, and more. SMC works by switching the control input between two directions, kind of like tapping the brakes and gas repeatedly, but in a smart way. This aggressive switching is what makes it strong, but it also causes chattering. We'll fix that in advanced version. Now that we built the institution, in the next video we'll go under the hood and code the basic SMC in MATLAB. We'll see how the control law is built and tested with disturbances. Thanks for watching. This is Safa. We're learning together, one concept, one line of code at a time.